Okay, so welcome back to this lecture, where the topic is this notion of Schurs Lemma. And I'll prove also the Schurs Lemma. And it's a very short little lemma that allows you to basically compare two irreducible representations to each other, that whether they are like isomorphic or not. So we will talk about this notion of isomorphism between two representations. And it's a very useful way because we can sometimes, like when we do the Fourier analysis and we want to represent the group, we want to somehow identify some of these representations to each other. That when we compute, for example, the Fourier coefficients of something, we basically are just computing what a single element of this class of representations that are equivalent to each other. And this lemma allows us to analyze this more efficiently. So before I state the lemma, so this is the going into the notion of Schurs lemma, and let's call it morphisms. So I need to define the notion of a morphism. So let rho 1 is a mapping from U V rho 1 and rho 2 mapping from G U V rho 2 be irreducible representations. Actually, they don't need to be irreducible. They could be any representations. So in this case, they are unitary representations, but I'll do it in this context now. And then we say that a map phi from V rho 1 to V rho 2 is a morphism if, first of all, phi is linear, and second of all, it conjugates with the action of the representation in the following way: that if you have this phi and you take you could multiply. It's a linear map, so these two matrices, once you multiply them as a mapping, then you get the same as rho 1 of x, and you get psi for any x in G. So that's the notion of a morphism. So what does the morphism mean basically? Is if you notice like a notion of a commuting diagram. So you could have here V rho 1, and then you have V rho 1, and then you have V rho 2 and V rho 2, and then you have a mapping of here to here. And where we basically have two ways to going through. So here you have the mapping, which is the representation. Also, sorry, there should be a rho 2 here. The rho 2 of x, and here we have a rho 1 of x. So remember, each of them are linear mappings between these two vector spaces. And then here you have a phi that maps the V rho 1 to V rho 2. And so basically they say that that i.e. this diagram commutes. I think this is something that you might have seen in algebra if you have done like some algebra, these kind of commuting diagrams. So basically it means this conjugation happens for any x in G. This diagram commutes. Okay, so once you have a morphism, we can talk about isomorphisms. So we say that this rho 1 and rho 2 are isomorphic if there exists a morphism phi, well, I think I use psi, or the phi, let's put phi rho 1, y rho 2, such that phi is invertible with psi minus 1 from V rho 2 to V rho 1, so that's when the inverse exists, is also a morphism between now row 2 to row 1. So this is the notion of an isomorphic thing. So basically, you could have a morphism, which could be like a factor in some sense, that you're like projecting to something. But here the isomorphism is that you can get to both ways. You have an invertible mapping in this way. And Schurs Lemma basically allows you to like understand these notions of what does it mean to be like isomorphic to a different types of representations. So the one way to write this, I could write this in this way that so let's call the Schurs Lemma, which is written as follows. So I use this. I think I'll use the definition I have. So so it has two properties. So one is that if row 1, which is a unitary representation, let's say from row 1, and row 2, which is a G, U, V row 2, are irreducible, and we have that phi V row 1 to V row 2 is a morphism, then this psi, phi, or whatever this phi, has to be equal to the zero matrix for any whenever this row 1 and row 2 are not isomorphic. So if you have a morphism, something, and and they are not isomorphic, the only possibility is that this phi is equal to 0. So that's the first part of the Schurs lemma, that if you have two irreducible representations and there's a morphism between them, but you are assuming that they are not isomorphic, so there doesn't exist such an inverse that is for this mapping phi, then it's actually the only possibility is that this mapping is 0 in this case. So that's the only possibility in the case. And the 2 is kind of like the case when row 1 and row 2 are the same. So let me write down this version. So let row from G to GL, let's take the unitary matrices, V row, be a irreducible representation and phi from V row to V row a morphism, then this implies that if this is irreducible representation, you have a morphism from the vector space to itself. So i.e., remember that if it's a morphism to itself, that means that this psi row of x is a row of x phi for every x in G. Then that implies the Schurs lemma is just saying that this phi has to be some constant multiple of the identity matrix for some actually this is for some constant kappa. That's the only possibility that this could happen in the sense. So if you think about the irreducible representation, you have a morphism. Okay, for example, you have the identity matrix. That could be that's a morphism, so it intervenes with the representation like this. So if phi would be an identity matrix, then this would be I from row x is equal to row xi. That's always true. So it is the constant is equal to 1. But the nice thing about the Schurs lemma is that you can take any morphism. As long as it satisfies that property, then the only possibility is that it somehow stretches the space to every direction uniformly. So it is a diagonal matrix with the same diagonal at every point. So it's a constant multiple of the kappa. So the kappa actually does depend on the phi in this way. So the proof of this, let's do the proof. The proof goes as follows. So we only prove this part 2. So the part 1 actually has a very similar proof as part 2 with the 2 different representations. So we just prove the part 2, and I'll leave to you to check out how do you use the similar idea in the proof of the first one. So how do you get this part 2? So let's write first just v, like shorten this notation, that's v rho, and we let lambda, some complex number, be an eigenvalue of this phi, i.e. there exists some v which is non-zero such that this phi v0 is a lambda v0. So this this is in v such that this happens. And what I claim now that this eigenspace, which I call is all the vectors. So this v in v such that lambda v is equal psi v phi v is equal to lambda v is rho invariant. So this is what I'm claiming now. So remember, the rho invariance meant that the rho of x at e lambda is equal to e lambda for any x in G. So we have fixed this v0, so we got an eigenspace, so we have this eigenspace, and the corresponding all the eigenvectors in this space is a rho invariant space. So notice now that as v0 is not equal to 0, and v0 belongs to e lambda, this implies in particular that e lambda, we know that e lambda cannot be equal to the trivial subspace of just a unit here. So this is important, that because we have an irreducible representation, and I'm claiming that we can prove this property, it's an invariant subspace, and you actually have that you have a non-zero element in there. So we know that it's if it's a rho invariant and it's a irreducible representation, the only possibility is that e lambda is everything, and then that can be deduced to actually to get a claim from that. So I will show that at the end, but the main thing is really this, that to prove that this is rho invariant, that implies the kind of the claim we have. So how do we prove that rho invariance? Proof of a rho invariance is as follows. So how do we prove a rho invariance? So we need to take a general element here. So what we can do is that we take v in this e lambda, and we are done if we can prove that this, if you take rho x v, okay, and I will actually prove its eigenvalue with this. So we are done if we can prove this. While you map this into this vector, you get the lambda rho x v. So that implies, because this is equivalent of saying that rho x v belongs to e lambda. So how do we prove this? So we actually can subtract from both sides. So we can actually subtract the kind of basically subtract from both sides the lambda rho x v. So this is equivalent to saying that the phi rho x, and maybe if I subtract the lambda, I think I take in this way rho x. This is equal to, if we apply to v, this is equal to 0. But then, how do we prove this one? Now we can use the morphism relation. So remember what morphism meant, the definition of the area. Let's go back to the definition. well, we have it already in the statement of the Schurs Lemma. So remember, morphism meant that, look at this, so we have the row X has this property that if you take the phi from the left and row X as a matrix product, you get the same as row X from the right for any X in X. And we have this here. We have here, so we can actually change this, that this is equal to row X phi, as this phi is a morphism. So now we know that this is actually equivalent to, if you open this up, you can get row X, and you have the phi from the right, and then you have the lambda rho of X V. That's what the statement is. So how do we prove this one then? Well, now we can actually just go into the definition of the eigenvalue. So we can actually see that this element here, if you really want to open this up, this is just equal to rho of X times, you take phi, and minus lambda of the identity matrix. That's the what this is, this element here. Because we are basically, this is a scalar, so this is a scalar. So we can take this as a multiplication of the identity matrix. So we can think about the scalar. So when we have the here we can take that the lambda rho of X is equal to lambda I rho of X. So you can also think about this as a rho of X times lambda I, if you multiply it from the right in this way, because it's an identity matrix. So that's why we have this property. So this is actually equivalent to this being 0. But what we know here is, if you look into this definition, you can still open this up if you want really to be careful. So this is phi of v minus lambda v. This is 0, but we know that this is equal to 0 as the v belongs to E lambda. That was the assumption. So what we have now, but now rho of X, this is true. So this is basically equivalent to rho of X being equal to 0 is equal to 0, which is fine, because as is true as the rho of X is V to V is a linear map for any X in G. So it maps every element into 0. So you have a linear map, so the zeros are mapped into 0. So that's why you have this Schurs Lemma holds. Or maybe this is like a half the proof. This is the proof of the invariance. So now as so we have that rho X E lambda is equal to E lambda for any X in G, which implies, as the E lambda cannot be equal to this trivial subspace, that E lambda is equal to the whole space, since the rho is irreducible. So that's the thing. And now this implies now that as the remember that this is the eigenspace of the whole thing. So this is the one eigenvector, and we know that the eigenspace is everything. So this everything is generated by a single thing. So this is only possible if the phi is equal to this lambda times I. So this constant that I constructed is given by this eigenvalue that I have written. Well, actually, for some, yeah. If everything holds true. So if the lambda is, for example, non-zero example, then I can get this into this state. Okay, so that's the basic idea of the proof, and now you can kind of maybe. Well, next time actually you can see how this actually helps with a lot of things. It looks a bit like simple, that the statement is only saying the following, that this once you have a morphism, between two spaces or some irreducible representation, that the morphisms can only look like this. But typically these morphisms arise in many of the Fourier analytic theory. So there will be some constructions of morphism, like for example the Fourier transform will actually become some type of a morphism. And if you would want to compute the Fourier transform, you can use Schurs Lemma to deduce that it's just a diagonal matrix with some constant. And then the constant can be constructed from the trace, for example. That's one way to find out the constant. So I'll come into this in the next lecture, so you'll be able to see the kind of main definitions. So in the next lecture I plan to go into the Fourier transform a bit more carefully. So I'll see you then.